And whenever you're ready, oh, thank you, Joe. Always a step ahead of me. So welcome back. You guys are great, troopers. Thank you for sticking with me. For those of you who are watching this as a recorded session, welcome. And thank you for joining us. My name is Helen Chan. I will be your moderator for this session, along with Mark Goldstein and Jill Packham. Okay, so you are joining us for the third live session that we're recording for this afternoon, which is on lesson 21.2, and it is about squares and square roots. Okay, so for the next 30 minutes, that's what we'll be doing, and this is recorded for later viewing, or if you want a refresher of the highlights on these lessons. Okay, so there's our schedule. We are now in the third session that's highlighted in red there. We have one more session after this, which starts at 4:15 on time distance graphs. If you are watching this as a pre-recorded session and you need to contact us for any assistance, just email one of us and we'll be happy to answer your questions. Okay, and we will be providing our contact information again later on at the conclusion of this session. Okay. All right, so this was our warm-up for the session. So Pat, again, has helped us fill in these, answer these prompts that we've been leaving on the whiteboard. So here, what you were to do was to draw different sizes of squares on the grid, and then record the side length and area, which we see that Pat has done nicely for us. So the question I want to ask here is, can somebody tell me what they see is the relationship between the side length, oops, let me get my finger there, okay, between the side length, okay, and the area of each square. Okay, look at each pair of numbers that Pat has written. The one that she wrote on the outside is obviously the side length, and then the one that she wrote inside the square is the area of that particular square. So what is the relationship? Oh, okay. So says square the side to get the area, Shelley says. Okay, Joe says that the side length squared is the area. Okay, a nice way to show the kid that the side square is area and the square root of area is side length. Good. Okay, yeah, and this is really where it comes from, the square. You actually physically have a square. Okay. So, so that was the warm-up, and oops, sorry. So we will probably refer to these later on in our session. What I'd like to do now is just quickly go over the goals for lesson 21.2. Okay. So in this lesson, we'll be linking the geometric concepts of side length and area of a square to algebraic concepts of squares and square roots of numbers. Okay. And we're also going to be approximating the square root of a whole number by locating it between two consecutive integers. And then we're going to use those fractions, we're going to use fractions and decimals to close in on that approximation. Okay. This page is actually not filled out in the student pages. This is SP11 in the week 21 student packet. I've just filled out the last two rows there for time efficiency here. And the purpose of this is for students to have a quick reference when they're working on finding square roots throughout the lesson. Okay. One way I think that you can save time instead of like spending a whole, like a lot of time for each student to work on this page and figure out every one of these answers, is you can make a chart and a poster and just put it on the wall in your classroom, and just make this what is it, a 5x5 grid, and then as the students figure out the answer, they can just take a post-it or just take a marker and fill in the answers there. So everybody has a way of referencing, a quick way to reference these perfect squares. Okay, so that's one way that you can quickly go through and focus on the rest of the pages rather than on this. Okay. So right now, just real quick, let's fill out the third row there from 11 squared to 15 squared. Okay. Shelly, do number 11 squared. Pat, do 12 squared. Mark, you do 13 squared. Joe, you do 14 squared. And I will do 15 squared. Okay, there, see? That was quick. Teamwork works. So you can see how much time you can save in the classroom too. Okay. If you have your student packet open to SP12, you don't have to, but if you do, you'll notice that this looks a little bit different than what's on the page. It's because in the students actually have to fill in the numbers. Let me get my little finger going again. They actually have to fill in the numbers along the number line, and also to locate the square roots on the number line. Okay, but again, I've done this ahead of time to be more efficient. Okay, so now why is here's a question. Okay, why is the distance between the square root of 1 and the square root of 4? Why is that distance the same as the square root of 25 and the square root of 36? Can we see this on the number line? Because their square roots differ by 1. Exactly. Because if you look at the square root of 1, that's 1, and the square root of 4 is 2. Okay, so the distance between 1 and 2 is just 1 unit. Same thing here. Even though they might not seem like they're only 1 unit apart, but the square root of 25 and the square root of 36, okay, it's just 5 and 6, and the distance between that is also 1. Okay. All right. Now, okay, let's see if we can estimate the location of the square root of 27, which is number 2 right here. Okay. So these right here, okay, we already have them on the number line. But if I were to locate the square root of 27, how would I do that? Okay. If we look at that, if we look at our number line, we can see that the square root of 27 is going to be somewhere between the square root of 25 and the square root of 36. Okay? We can even say that the square root of 27 is going to be closer to the square root of 25 than to the square root of 36. Do you agree with me? Click a happy face if you do, and sad face if you don't agree with me. Okay, so we all see that, right? Now, based on our previous observation, we can also say that the square root of 27 is somewhere between 5 and 6, although it's going to be closer to 5 than it is going to be to 6. Okay, so our answer, okay, the square root for the answer for the square root of 27 is going to be something less than 5.5. Do you agree or disagree? Show by happy or sad face. Okay, good. So now we can estimate the decimal part, okay, by asking, okay, what fraction of the distance from 25 to 36 does 27 represent, okay? And the way we find that out is we can subtract, as we show here, okay? We can subtract 27 minus 25 divided by 36 minus 25 on the denominator, okay? And when we do that, we're going to get, and I can fill this out, we're going to get 2/11, okay? So that's the fractional part, okay? So as Joe is doing right now is now we can say, okay, therefore, the square root of 27 is going to be about 5 and 2/11, okay? And if you actually, if you check the square root of 27 on a calculator, you're going to get, and I'll type this up because I have it written now for you. If you do it on the calculator, it's about 5.196, okay? And if you type 5 and 2/11 on the calculator, it's going to be 5.18 repeating, okay? So you can see that our estimate is actually really good, okay? Does that make sense so far? Okay, great, okay? So the next slide, what I'm going to do is now, I'm going to show you two ways, two strategies, two visuals to support linear interpolation, which is what we did there to find out the fractional part, the decimal part of the square root of 27, okay? Here's the first strategy, and this is using a number line, okay? So what we do is remember, okay, you have to remember that we're trying to find the fractional part to the square root of 27, okay? And remember that it was located between square root of 25 and 36, okay? So we draw a number line here, starting with 25, all the way to 36, okay? And then we also locate 27, okay? And so we can see here that the distance between 25 and 27 is 2 units, okay? And the distance between 25 and 36 is 11 units, okay? So that explains why, the distance, so now we can write that as a fraction, okay, as 2/11, okay? Is this helpful to you? And yeah, Mark, thank you for remembering that. There is a handout because this is not in the teacher guides or in the student pages. We will be sending you, Pat, an email with with these pages that are not in your materials. Okay. Okay. So now, why does linear interpolation work? Okay. So if we look at this, okay, this is actually the graph of the equation for square root of x, okay? But we're only looking at the upper half because we have to look at only the non-negative numbers, okay? Because the other part would be like, right here, okay? And that's, we don't want those, so we're just only on the positive side, okay? So now, if you go from left to right, the curve, actually, as you go out more and more, it looks more linear. Okay, so that means that when we go further out, like to infinity, positive infinity, it's going to look more and more like a horizontal line. And that's why, as you saw in the previous page, that's why we can kind of use this this number line as a way to help us estimate the fractional part of that the square root of 27. Okay, because when you go out to infinity, this one is going to be pretty close to a horizontal line. Okay, now here's the second way, the second visual strategy to help us support linear interpolation, and this one is using an area model. Okay, what we do here, remember again that the square root of 27 is somewhere between the square root of 25 and the square root of 36, right? So then what we draw is we draw a 6 by 6 square, okay? And inside that, we shade in a 5 by 5 square, okay? Thank you, okay? So the larger square has 36 units, okay? And the smaller shaded square has 25, okay? And now if you look at the white ones that are left over, kind of like, yeah, between the two overlapping squares, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 leftover squares, right? The white squares. So that's where that 11 comes from. And the 27, okay, you're just claiming like 2 extra squares here. So that's why we came up with a 211. Okay, and that explains why the square root of 27 is about 5, right? 5 and 211. Okay, and again, I showed you this in the previous slide that if you do this on the calculator, it turns out to be a 5.18 repeating, whereas, you know, square root of 27 straight on the calculator is about 5.196. So it's pretty good. Okay. Yeah, okay. Mark is saying that remember that the explanation using the graph of y equals square root of x is only for mathematical insight. Yes. Okay, you have a teacher math background for the teachers that is a lot more comprehensive in your teacher guide. That's for the teacher mathematical insight only. Okay. These kinds of things. Okay. This one, and this one is more, those are for the kids, okay? Do you have any questions? No, okay. All right, so let's move on, okay? Here's another one, okay? Let's try this one now. We just did one, an example using 2 different ways. The linear, using the number line and then the area model to help us estimate the fractional part of the square root of 27. Now let's try square root of 40, okay? Okay, and this is why having the that page with the perfect squares filled out would be helpful, but I think we can figure it out. Okay, so the square root of 40 is between what 2 perfect squares? Okay, and somebody's probably filling it out. Okay, it's going to be between 36 and 49. Okay, so I'm going to put SQRT 36 for square root. Oh, thank you, whoever's doing that. But let's put SQRT. Okay. Thank you. I'm going to delete my thing so that we're not overlapping. And then, okay, and the square root of 36 is 6, and the square root of 49 is 7. Okay, now, is the square root of 40 going to be closer to the square root of 36 or the square root of 40? 36. That is correct, okay? Which means that the square root of 40 is going to be closer to 6. Happy face if you agree, sad face if you disagree. Okay, so now when we estimate the decimal part of this, of square root of 40 as a fraction, again, we can do this. And I'll attempt to do my line here. So you go from 36 to 40 for your numerator, and then from 36 to 49 for your denominator, okay? And then when you write it here, you're doing 40 minus 36. Oh, thank you, Joe. I would just stop writing because I think you do a better job. 40 minus 36, and then 49 minus 36 for the denominator, okay? And that, I believe, turns out to be 4/13. Is that correct? Somebody check for me. 4/13, right? Okay. So, and I've done this ahead of time for time, to save time. If you work out, so therefore, square root of 40 is about, and I'm going to have Joe fill this in, okay? Square root of 40 is about 6 and 4/13, which I'll put the calculation there, 6.308, okay, if you do that on the calculator. And if you punch in square root of 40 on the calculator, it is about, rounded to 3 decimal places, 6.325. Okay? Is that clear? Does that make sense, everybody? Okay. Yeah, I don't care about the rest of you. I just care about that. Okay. So now let's try to do the same one, but using the area model. Okay. So while Jill is helping me fill out these two rows up here, because we already did that at the in the previous slide. Okay. Let's focus on this the square right here. Okay. So again, remember that the square root of 40 is somewhere between the square root of 36 and the square root of 49, right? So what we did here is we drew a 7 by 7 square, which is a big one, okay? And then the shaded one is our 6 by 6, okay? Right? So then, for the square root of 40, well, we already have 36 shaded, right? So we just need to shade in 4 more X's down here. Thank you. That was clever. Okay? So now, what we do, and I'll do this part, Joe, okay? We take the 40 and we subtract 36, and we get 4. And then 49 minus 36 equals 13. Or you can see that in our square, that before Joe shaded the little yellow squares here, that there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 blank, 13 white little squares. And to get to 40, we needed to shade in 4 out of those 13, and that's how we got the 4 13s here. Okay? Any questions? Do you like, which one do you like better, Pat? Do you like the linear model, or do you like this area model? Do you like the area? Me too. I think Mark likes the linear, right, Mark? Or was I wrong? Sorry. Is it okay with everyone? Oh, you don't really care. Okay, Shelby likes the linear. Okay, I got those two mixed up. Okay, I'm going to move on to the next slide. Okay, and I'm doing great on time. Okay, this one is taken from SP14. Okay, and you actually have a lot more problems on that page than these. I just kind of picked the first few problems for us, along with the first row, which is already filled out. Okay. So what I'd like to do is assign each one of you to a problem, and just go ahead and fill in the table here. Don't worry if you can't get them all filled out, because I don't know if everybody has a calculator. What I can do is I'll fill in the calculator check for you, okay, while you guys are doing that. But you go ahead and fill out columns B, C, and even D if you want, okay? And you might have to do some of the work on a paper on the side, on a scratch piece of paper. Just try it, okay? And we'll see. And I'll have Joe. Let's see. Why don't we set up the timer again for 1 minute, okay? And let's have Mark do number 3. This one, okay? We'll have Pat why don't you try number 4? And Shelly, you will try number 5. Okay? And when Joe is ready, we can set up the timer. Thank you. And I will fill out column F for everybody. Okay. Looks like you guys all have a good start. Okay. Okay, let me just check Shelly's real quick here. This one is actually about, on my calculator, is about 4.44 for repeating. Okay. For Pat, let me just double check real quick. Pat, for you, yours is about, if I am looking at the numbers correctly. So you can kind of compare column E and column F to see how close we are to the calculator check. Okay, column E is using your fraction estimate, and then column F is actually just straight from the calculator. So you can see, oh, maybe I did something wrong, Mark. How come yours is so way off? Okay, somebody's checking that for us. Yeah, but you can see how Shelly's is pretty close, and so is so is Pat's. And then we're trying to find out what happened to Mark's. I think it's probably just some just minor, typing error there. But oh, you made a mistake. Okay, and you fixed it. Okay. So Shelly's saying in the chat box that the larger the original number, the closer the estimate, because the graph curves at the beginning, whereas I think what she's going to say is whereas, later on, as you go out further, it starts looking more and more like a straight line. Is that what you were about to say, Shelly? Yeah. Okay. I think this is really cool discovery. Do you have any questions? Does anybody have horrible memories from junior high of having to do something very similar to long division to find out the square roots of non-perfect squares? I remember doing that in 7th grade, but I can't remember what I did. I just remember having to do something like that to find out square roots. Yeah, Joe too. Yeah, I think this is just so, it makes so much sense the way it's laid out here. Do you read that? Oh, okay, you're saying it. Oh, yeah, sure, Mark. Okay. Okay, so yes, but you wonder if the kids will appreciate this method. Okay, yeah. So maybe we should show them the ugly way and then show them here's a nicer way to do it. Okay. All right. It is 4 o'clock, and I am so proud of myself because I did this. I finished right on time. Okay. We have one more session after this at 4:15. If you are still alive, please join me for the final session this afternoon. I'm having a lot of fun. I hope you are too. And now I think I'm just sounding like a TV show. So I need to go and take a break. See you in about 15 minutes. And Mark, if you can, you don't need to